Hi everyone, welcome to this talk on engineering reliable mobile applications. My name is Pranjal and I'm an SRE program manager at Google, and I'm speaking to you from San Francisco. Here's a little bit about myself. I think Shireen introduced me already, but I've been Google for about 5 years, and I've worked on client infrastructure teams, Firebase SRE, and I also got the opportunity to work on some Gmail spam abuse domain teams. I've co-authored 2 publications. So one of them is Blameless Postmortem Culture in the second SRE book. And then another one is Engineering Reliable Mobile Applications that I've condensed into a talk and then I'm presenting today. And both of these are available online for free if you want. And then before joining Google, I was in not a very prescriptive role. There was a small company. I used to do a lot of things for them, but that could be a bad thing, but it helped me develop a lot of skills that now I can use in my current company. And I also have a little puppy. His name is Teddy. And I also like exploring different cuisines and traveling, and I cannot wait to hop on a plane when COVID is back behind us. So a little bit of agenda for today. I'll briefly cover the basics of traditional SRE, quick 2-minute intro, and then compare and contrast it with what it means to be SRE for mobile. I'll go deeper and talk about several distinct challenges like scale, monitoring, control, and change management. Then I'll go into high-level strategies for developing resilient native mobile apps. I'll follow this by 3 case studies, so actual outages that happened and then what we learned. And then in the end, I'll summarize key takeaways. So now I assume most of you already know this, but to set some context, especially for folks who may be new to the industry, SRE, think of it as a specialized job function that focuses on reliability and maintainability of a system. SRE would mean site reliability engineering. It's also a mindset. So the approach to work is that of constructive pessimism, which means you hope for the best, but you plan for the worst, because hope is not a strategy. And of course, primary responsibilities are to ensure health of a dedicated service in terms of availability, latency, efficiency, emergency response, change management, monitoring, capacity planning, etc. Now, to talk about the core topic, which is availability, it's most commonly assumed that we're talking about server-side availability when we speak of SLAs or 99.9% of something. And most SLAs have been traditionally bound by server-side availability. So 2 or 3 nines of server uptime. But the problem with relying on only server-side availability is an indicator of service health is that users perceive the reliability of a service through the devices that they have in their hands. Now, we've seen a number of production incidents in which server-side instrumentation taken by itself would have shown no trouble, but where a view inclusive of the user experience was reflected, it was showing end problems. So for example, your server stack is successfully returning what it thinks are perfectly valid responses, but users of your app are seeing blank screens. Or I'm sure this has happened to you, it happened to me many times. So let's say you're in a new city, you open your Maps app, and then the app just crashes, or the server does not receive any request at all. Or sometimes after your application receives an update, although nothing is visibly changed on the UI side, but you experience significantly worse battery life than before. Now, these are all examples of issues that cannot be detected by just monitoring our servers and data centers. Now, we can compare a mobile app to a distributed system that has billions of machines. The scale is just one of the many unique challenges. Things we take for granted today in the server world become very complicated to accomplish for mobile, if not impossible. So here are some of the challenges. So in terms of scale, think about this. There are billions of devices with thousands of device models, hundreds of apps running on them. Each app has its own multiple version. So it becomes more difficult to accurately attribute degrading UX to unreliable network connections, service unreliability, or external factors. Now, all of this combined together makes for a very complex ecosystem. Then challenge number 2 is monitoring. We need to tolerate potential inconsistency in the mobile world because we're trying to rely on a piece of hardware that's beyond our control. There's very little we can do when the app is in a state in which it cannot send information back to you. Now, with this diverse and complex ecosystem, the task of monitoring every single metric has many possible dimensions with many possible values. So it's infeasible to monitor every combination independently. We must also consider the effect of logging and monitoring on the end user because they pay the price of resource usage. So let's say battery and network, for example. Now on servers, we can change binaries and update configs on demand. In the mobile world, this power lies with the user. In case of native apps, after an update is available to users, we cannot really force them to download a new binary or config. Users can sometimes consider upgrades to be indicators of poor quality software, and they can assume that all upgrades are just bug fixes. Now, if there's a bad change, one's immediate response is to roll it back. We can quickly roll back servers, and we know that the user will no longer be on the bad version after the rollback is complete. On the other hand, it's close to impossible to roll back a binary for a native mobile app on Android and iOS. Instead, the current standard usually is to roll forward and hope that the affected users will upgrade to the newest version. Now, considering the scale and lack of control in the mobile environment, managing changes in a safe and reliable manner is one of the most critical pieces of managing a reliable mobile app. Now, in this section, I'll talk about some concepts that are not foreign to us, mentioned in the SRE book. I think you use it in your day-to-day life, but I'll put them in the context of mobile and then discuss some strategies to tackle them. Now, availability is one of the most important measures of reliability. So think about a time when this happened to you. You tapped on an app icon, the app was about to load, and it vanished. Or a message displayed saying that your application has stopped. Or you tapped a button, app did not respond, you tried again, still didn't respond. Or you waited for something to load and then eventually abandoned it by just clicking the back button because it was so frustrating. Now, these are all examples of an app being effectively unavailable to you. So you, the user, interacted with the app and it did not perform the way you expected. So one way to think about mobile app reliability is its ability to be available, servicing interactions consistently well relative to the user's expectations. Users are constantly interacting with their mobile apps. And to understand how available these apps are, we need on-device, client-side telemetry to gain visibility. If you cannot measure, you cannot improve it. But while we're doing that, it's important to remember that privacy and security are topmost concerns when we develop our monitoring strategy. Now, who doesn't love real-time metrics? So the faster one is able to alert and recognize a problem, the faster one can begin investigating. Real-time metrics can also help us see the results of our fixes and get feedback on production changes. Most incidents have a minimum resolution time that's driven more by humans organizing themselves around problems and determining how to fix them. For mobile, this same resolution time is also affected by how fast we can push the fix to users' devices. Now, most mobile experimentation and config at Google is polling oriented, with devices updating themselves during the right times of battery and bandwidth conservation. This means that even after submitting the fix, it might be several hours before client-side metrics can be expected to normalize. Now, telemetry for widely deployed apps is constantly arriving. So despite this latency, telemetry from some devices may have picked up the fix, will arrive shortly afterward. Our approach to design metrics derived from device telemetry is to include config state as dimension. You can constrain your view of the error metrics to only the devices that are using your fix. This becomes easier if client changes are being rolled out through launch experiments, and you can look at the experiment population and the experiment ID together to monitor the effect of your changes. Now, when developing an app, we have the luxury of opening a debug console and looking at fine-grained log statements to inspect app execution and state. However, when it's deployed to an end user's devices, we only have visibility into what we've chosen to measure and transferred back to us. So measuring counts of attempts, errors, states, timers in the code, particularly around key entry exit points and business logic, can provide indication of the app's usage and current functioning. Another good idea is to run UI test probes to monitor critical user journeys. This entails launching a current version of the binary on a real or emulated device, inputting actions as a user would, and asserting that certain properties hold true throughout the test. Now, what resource enables your phone to be mobile in the first place? It's the battery, making it one of the most valuable resources of a mobile device. Then there are other precious shared resources like CPU, memory, storage, network, and no application wants to misuse these shared resources and get negative reviews. Efficiency is particularly important on lower-end devices in markets where internet or data usage is high cost. The platform as a whole suffers when shared resources are misused, and increasingly the platform itself needs to place restrictions to ensure common standards. So one such example is a program called Android Vitals that help attribute problems in the app. So sometimes internal apps have been blocked from releasing for battery regressions as low as 0.1% because of the negative effect on user happiness. Any expected regressions need to be released after careful considerations of the trade-off by feature would provide. Now, I'm going to spend a little bit longer on this slide because there's a lot to talk about. Many of the best practices while releasing client-side applications are based on the general SRE principles that you may have already heard of and you actually use. So this is one of the most critical pieces of the mobile ecosystem because a single new faulty version can erode user trust, and they may decide to never install or even upgrade your app again. Rollbacks in the mobile world are still near impossible, and problems found in production are irrecoverable, which again makes proper change management very important. So the first strategy is a staged rollout. This simply means gradually increasing the number of users an app update is released to. This allows you to gather feedback on production changes gradually instead of hurting all your users at once. Now, one thing to keep in mind here is internal testing and testing on developer devices does not really provide a representative sample of the diversity that's out there. If you have the option to release to a subset of beta users, it will help the pool of devices and users to become a little bit wider. Now, one issue with staged rollouts is the bias towards newest and most upgraded devices. So metrics such as latency can look great on newer devices, but then the trend becomes worse over time, and then you're just wondering what happened. Folks with better networks may also upgrade earlier, which is another example of this bias. These factors make it difficult to accurately measure the effect of a new release. It's not a simple before and after comparison of metrics and may require some manual intervention and interpretation. So a better way to release changes is via experiments and conduct A/B analysis as is shown in the figure. I hope you can see it. Font is a little bit small. And wherever possible, randomize the control and treatment population to ensure that the same group of people are not repeatedly upgrading their apps. Now, feature flags is another option to manage production changes. The general best practice is to release a new binary with new code and turn the feature flags off by default. This gives more control over determining release radius and timelines. Rolling back can be as simple as turning down the feature flag instead of building an entire binary and then releasing it again. Now, this is with the assumption that rolling back the flag is not breaking your app. Now, one quick word of caution in terms of accuracy of metrics is to take into account the effect of upgrade side effects and noise between the control and experiment population. The simple act of upgrading an app can introduce some noise as the app restarts. One way to address this is to release a placebo binary to the control group, which doesn't really do anything, but it will also upgrade or restart, thereby giving a more apples to apples comparison of metrics. This is, however, not a very ideal solution and has to be done with a lot of caution to avoid negative effects such as battery consumption and network usage. Now, even after doing all of the above and putting all this governance in place, the power to update their app still lies with the user. This means that as newer versions keep releasing, older versions will continue to coexist. There can be many reasons for not updating. So some users disable auto updates, sometimes there's just not enough storage. On the other hand, privacy and security fixes are strong motivators for upgrades. Sometimes users are shown a dialog box and they have to upgrade, there's no choice. As client apps grow and more features and functionalities are added, some things may not be doable in older versions. So for example, if you add a new critical metric to your application in version 2.0, that metric will only be available in version 2.0 and up. So if SRE is supporting the app, it may not be sustainable for them to support all possible versions of a client, especially only when a small fraction of the user population is on the older version. So possible trade-off could be developer teams can continue to support older versions and make business or product decisions around supporting timelines in general. Now, we focused a lot on the client side so far. This side is a quick reminder that making client changes to an app can also have server-side consequences. Now, your servers may already be scaled to accommodate daily requests, but problems arise when unintended consequences occur. So some examples could be time synchronization requests or a global event causing a large number of requests to your server suddenly. Sometimes bugs in new releases can increase the number of requests and overload your servers. Now we'll see an example of one such outage in the following section, which brings me to case studies. So in this section, we address the topics covered in the previous sections through several concrete examples of client issues that our teams have encountered. The slides also note some practical key takeaways for each case study, which you can then apply to your own apps. So this first case study is from 2016, when AGSA, which means the Android Google Search app, tried to fetch the config of a new doodle from the server, but the doodle did not have its color field set. The code expected the color field to be set, and this in turn resulted in the app crashing. Now, I hope you can see the graph clearly. Again, the font is pretty small, but what it shows is crash rate along a time series. So the reason the graph looks like that is because doodle launches were happening at midnight for every time zone, resulting in crash rate spikes at regular intervals. So the higher the traffic in the region, the higher the spike. This graph, because we are monitoring it, made it easy for the team to correlate issues to a live doodle versus an infrastructure change. Now, in terms of fixes, it took a series of steps to implement an all-round concrete solution. In order to fix the outage, first, the config was fixed and released immediately, but the error unfortunately did not go down right away. This was because, to avoid calling server backends, the client code cached the doodle config for a set period before calling the server again for a new config. So for this particular incident, it meant that the bad config was still on the user's devices until the cache expired. Then a second client-side fix was also submitted to prevent the app from crashing in this situation. But unfortunately, a similar outage happened again after a few months, but this time only the older versions without the fix were affected. Now, after this reoccurrence, a third solution in the form of server-side guardrails were also put in place to prevent a bad config from being released in the first place. So some key takeaways here are that client-side fixes don't fix everything. In particular, there are always older versions in the wild that may never get updated. So whenever possible, it's important to also add a server-side fix to increase coverage and prevent a repeat incident. And then second is good to know your app's dependencies. It can help understand what changes external to the app may cause failures. It's also good to have clear documentation of your client's dependencies, like server backends and config mechanisms. Now, this is another case study, again, AGSA. So my team is responsible and on call for the Google search app. That's why I have all these examples. So this one was in 2017, and it was one of our largest outages, but a near miss of a truly disastrous outage, as it didn't affect the latest population version. So in this one, the outage was triggered by a simple 4-character change to a legacy config that was unfortunately not canaried. One of the things I mentioned in the change management slide. It was just tested on a local device, run through automated testing, committed to production, and was rolled out. So 2 unexpected issues occurred. First, due to a build error, the change was picked up by old app versions that could not support it. And second, the change was rolled out to a wider population than intended. Now, when the change was picked up by older versions, they started failing on startup. And once they failed, they would continue to fail by reading the cached config. Even after the config was fixed and rolled out, the app would keep crashing before it could fetch it. So this graph shows you daily active users of the app on the affected version range over a 2-week period leading up to and then after the outage. After scrambling for days, the only recovery was manual user action, where we had to request users to upgrade via notification, which prolonged the outage and resulted in bad user experience. So some key takeaways here are, anything that causes users to not upgrade is similar to accumulating a debt. Older apps are highly susceptible to issues, so the less successful app updates are, the larger the probability of a bigger population getting impacted by a backward incompatible change. Then always validate before committing. For example, caching a new config. Configs can be downloaded and successfully parsed, but an app should interpret and exercise the new version before it becomes the active. Cached config, especially when read at startup, can make recovery difficult if it's not handled correctly. If an app caches a config, it must be capable of expiring, refreshing, or discarding without needing the user to step in. And don't rely on recovery outside the app. Sending notifications to users has very limited utility. Regularly refreshing config and having a crash recovery mechanism is better. But at the same time, similar to backups, crash recovery mechanism is valid only if it's tested regularly. Now, when apps exercise crash recovery, it's still a warning sign. It can conceal real problems. So if your app would have failed if it was not for the crash recovery, you're again in some unsafe territory because the crash recovery is the only thing that's preventing failure. So monitor your crash recovery rates also and treat high rates of recoveries as problems in their own right, requiring root cause investigation and correction. So this last case study demonstrates how apps sometimes do things in response to inorganic phenomena, and capacity planning can go for a toss if proper throttling mechanisms are not in place. So this graph is a picture of the rate at which certain mobile apps were registering to receive messages through Firebase Cloud Messaging. This registration is usually done in the background, that is, if user install apps for the first time or when tokens need to be refreshed. Now, this is usually a gentle curve which organically follows the world's waking population. What we noticed one day were 2 spikes followed by plateaus. So the first plateau went back to normal, but the second spike and plateau that looks like the teeth of a comb on the right half of the graph represent the app repeatedly exhausting its quota and then trying again. Now, the root cause was identified as the rollout of a new version of Google Play services, and the new version kept making FCM registration calls. The right side of the graph, like the teeth of the comb, were from the app repeatedly exhausting its quota and then being repeatedly topped off. So thankfully, FCM was working fine for other apps because there was per app throttling mechanism in place, and then service availability wasn't at risk. But this is still an example of the consequences of scale in mobile. Our devices may have limited computing power, but there are billions of them. And when they accidentally do things together, things can go downhill really fast. So the key takeaway here was avoid upgrade proportional load. In terms of release management and uptake rates for installation, we created a new principle. Mobile apps must not make service calls during upgrade time, and releases must prove via regression metrics that they haven't introduced new service calls purely as a result of the upgrade. If new service calls are being deliberately introduced, they must be enabled via an independent ramp-up of an experiment and not a binary release. Now, this brings us to the last slide of the deck. So to quickly summarize this talk, usually I like to do 3 key takeaways, but there's just so much to unpack here. I'll do 5 key takeaways. So in terms of summary, modern product stack is only reliable and supportable if it's engineered for reliable operation all the way from the server backends to the app's user interface. Mobile environments are different from server environments and browser-based clients, presenting a unique set of behaviors, failure modes, and management challenges. Engineering reliability into our mobile apps is as crucial as building reliable servers. Users perceive the reliability of our products based on the totality of the system, and their mobile device is their most tangible experience of this service. Now, in terms of key takeaways, first, design mobile apps to be resilient to unexpected inputs, to recover from management errors, and to roll out changes in a controlled, metric-driven way. Second, monitor the app in production by measuring critical user interactions and other key health metrics. Design your success criteria to relate directly to the expectations of users apps move through your app. Third, release changes carefully via feature flags so that they can be evaluated using experiments and rolled back independent of binary releases. Fourth, understand and prepare for the app's impact on servers, including preventing known bad behaviors. Establish development and release practices that avoid problematic feedback patterns between apps and services. And lastly, it's also great to proactively create playbooks and have some incident management processes in anticipation of client-side outages and the impact it might have on your servers. And that's all. Thank you.